have the system now, and every part of the whole connection and parts down. So we are going to start with the generator. So we run the generator. So the gen is running, and the load is connected to the gen line. So what I'm going to do next is to connect the grid line. This is the wire for the grid line, and cut my socket. So let's check it out. The alarm indicates that the grid line is on. In 2 seconds, this will turn off. And as such, this actually went on because I have the grid line turned on, and after 10 seconds using the alarm indicator just to let me know that the grid line is on, after 10 seconds the system was able to switch into the grid line, and just as you can see, this man didn't turn off, but it was able to turn off the generator automatically. Turning off a generator automatically is one of the features which this project houses, and in this video I'm going to explain to you how the 3-source independent automatic changeover system works. This is an automatic changeover system that can change electric power between 3 common sources. These sources include the grid line, solar or the inverter line, and finally the generator line. For the scope of this video, I'm going to cover the following parts, which include the block diagram, the schematic diagram, Arduino programming, assembly, and finally the test run of this project. All the relevant design information will be made available at the end of the video, just as I will take you through on all of the building process and show you likewise how to make possible adjustments if you are going to be building upon this design. Starting off with the first part of this project, let's generate the block diagram. To generate the block diagram, I'll be doing this with my friend Chigozie. This is Chigozie, and he's the one that proposed this new design, just as he stumbled upon one of our prior projects here on YouTube, and he wrote to me indicating his interest to review this project with me. It's good to connect with people on social media platforms because of the project that I make, and consider subscribing to my channel if you have not, as these are many more projects I frequently build and publish here on my YouTube channel. Now back to the project. I generated the building block, which primarily include the sensor, comparator, and the switching. Each of these blocks have their subunit circuitry, which you can see here, and now I move to the next part of the project, which is the schematic diagram. Over here, I'm using Pro Tools simulation software for my design, and each of these sources houses a transformer which powers the relay for their live and neutral line. Beyond this powering functionality of the transformer, I'm also using the transformer as a voltage sensor for each of these sources. The AC voltage reading is gotten from this part of the circuit, and to better understand this design, I'm going to combine the assembly section of this project and the Arduino programming section all together in my explanation. I started off my assembly by soldering the components using the schematic diagram. Other discrete components were assembled just as I have them soldered. This is a 100k resistor which I have in a voltage divider network with a 10k resistor. This voltage divider network is the same in all of the sources circuit, just I use it to read the relative AC voltage. You can use any resistor value from 10k and above for this measurement, but ensure that the resistor connected to ground relative to the analog point is 1/10 of the other, just as I'm using 10k with respect to 100k. So let's say you are using a 20k resistor, it is obvious that you should use 200k respectively. Let me now explain how I got the AC voltage reading using only 2 resistors. For that, I will isolate other parts of the circuit which I have completed all the soldering and focus only on the sensor part of the circuit. For easy explanation, I will have these 2 circuits printed out. Here, we have our simple step-down transformer, full bridge rectifier, filter capacitor, voltage regulator, and finally our voltage divider circuit. This circuit is the same for the grid line, solar, and the generator line, so I will focus only on one just as I have it analyzed together with you. Starting off with the step-down transformer, just as the name indicates, it steps down input AC voltage to a lower AC voltage. This is the transformer that I use for this project, and as you can see from the description, when the input voltage is 220 volts, the output voltage is 12 volts for the center tap transformer that I used. If let's say the voltage at the primary turn is 250 volts, without doing any mathematical calculation, one should always or logically know that the step down voltage will be around 12 volts and above. And if the input voltage falls around 200 volts or let's say 180 volts on the primary turn, the step down output voltage will fall below 12 volts. Understanding this little concept about transformer which I've given, I will now say you've gotten 20% of the total explanation that I'm going to give. Moving on, this relative inducement or changes of the secondary voltage or secondary turn with respect to the primary turn or the primary input voltage is known as mutual inductance. For our objectives of using transformer as a voltage sensor, we need to analyze or know the relative output voltage of our transformer without making any estimation or guess, just as we did earlier. And to do that, we solve for this first case scenario. If 220 volts is equals to 12 volts, then 250 volts will be equals to output voltage. To find the output voltage X, we cross multiply and we are going to have 250 volts times 12 equals to 220 times output voltage X. Making X the subject, we now have 250 times 12 divided by 220, and this will give us 3000 divided by 220, which will equal to 13.6. 13.6 volts will be the output voltage on the secondary turn whenever the AC voltage on the input primary turn rises above 250 volts, and this is gotten without making any estimation or guesswork. Now, if you try solving for when the primary turn or the primary voltage is 200 volts, we will do the same thing. Instead of doing this log mathematics, we can easily get the ratio of change in voltage from the primary turn to the secondary turn of the transformer, and that is gotten by simply dividing the primary turn by the secondary turn. For the transformer that I'm using, I have 220 as my primary voltage and 12 volts as my secondary voltage. When I compute it, 220 divided by 12 volts, it will give me 18.33. And now, 18.33 is now what we call the voltage ratio for this transformer. Now, putting this voltage ratio at work, whenever the primary turn or the primary voltage on this transformer increases to any value, to know the secondary value, all I need to do is to divide the input primary voltage by the voltage ratio, and by doing that, I will get exactly the output voltage on my secondary turn. So let's put this back into this math. So whenever the voltage increases to 250, we divide it by 18.3, and doing this mathematics, we will exactly get 13.6 volts. Now, solving for when the primary turn or the primary voltage reduces to 200 volts. To find the secondary voltage, I'm going to input this same voltage ratio, and this is what I have. 200 volts divided by 18.3, and this will give me 10.91 volts. This simply means whenever the voltage drops down to 200 volts at the primary turn, the secondary voltage will be 10.91. Having this concept in mind, let's make the first adjustment on the code, and that will be line 19. Wait, I didn't put 18.3 as my turn ratio over here since I have 16.57. Why is that? This is because physical transformers are not so perfect as the manufacturers describe them. There are voltage drops and losses due to their limitation in the design. So, the best practice is to literally measuring your transformer turn ratio irrespective of its description, so as to find the proper ratio and to also utilize that on the project code. Now, to find my turn ratio, I remove every other components which include the microcontroller in order to have it not affect the reading I'm going to be getting on my transformer. Powering the transformer, I have my AC input as 175 volts, while the output AC voltage is 10.82. Now, computing this reading into my calculation, I have my voltage ratio as 175 volts divided by 10.82, and that will give me 16.57, and this is my voltage ratio. If I should take this reading while powering the relay and the microcontroller, my values will be affected, just as I have 180 volts as my AC input and 9.83 volts as my AC output voltage, instead of 10.82 or thereabout. Even though I'm running my lab with my generator, which its output voltage is not so stable, this particular calculation shows to you that it's not so cool to take your reading while having the components being powered, and as such, it's best to remove the transformer entirely from the circuit and have it well isolated while taking your reading. Next, the relative AC voltage, which in my case is 10.82 volts AC, is converted to a DC voltage using the full bridge rectifier circuit and the filter capacitor, which in my case is 2200 UF. Doing that, I got my output DC voltage up by the RMS value, which should be 1.41 times 10.8, and this should equal and give me 15.2 volts. But in reality, I got 13.3 volts, and this is likely due to the material type of my diode or my capacitor. So I deduced my RMS ratio by simply solving 13.3 divided by 10.8. That gave me 1.22. This value is what I imputed on my Arduino code. Finally, the output DC voltage 13.3 volts is divided by the two resistors 10K and 100K, and the output for this division is gotten using this formula. Voltage output equals to R2 times Vn all over R2 plus R1, and solving I now have voltage output equals to 10 times 13.3 divided by 10 plus 100, and this will give me 133 divided by 110, and finally I now have 1.2 volts. Measuring this value on the microcontroller analog pin, I got 1.16 volts, and this is equivalent to 1.2. So to cater for this tiny voltage loss due to the resistor material type, I added 0.29 onto my code. With the calculation that I made using these resistor values, this resistor network can read AC voltage up to 500 volts without allowing its relative DC voltage on the analog pin of the microcontroller exceed 5 volts. And for reliable voltage reading and a precise reading also, I would recommend you use this particular sensor for measuring of voltage from 0 to 350 volts AC. With that being said, let's now go through the Arduino code for this project. Here, I included the library for the LCD display. I declared the AC voltage sensor input pin on the circuit. These are the variables for the voltage reading, and here I have the input and output pin assigned for each sources. In the void setup function, I fully declared each pin out and their corresponding state of either input or output. On the setup, I turned all the output initially off, and here I initialize the serial monitor and the LCD display. Here on the void loop function, I made essential calculations in converting my voltage reading from the voltage divider network to its relative AC input for each sensors. And finally, I used the if statement to monitor and compare each sources as well as trigger the corresponding output. Uploading the code on the board, the project is now ready for test. Connecting the LCD and having it well in place, I powered the board using a 9V battery. Just as you can see, all sources are unavailable, and as such, the reason for the data showing on the screen. To power any of the sources, I soldered the secondary terminal of the transformer to the bridge diode. And this is for the primary source, which I'm going to be connecting to my grid line. I used an extendable wire to connect the transformer to the AC line, and once I powered the board, I got the power line detected by the microcontroller. Just as you can see, the voltage value was almost accurate when you compare my multimeter reading to that of the LCD and also on my power supply. Now, connecting all the sources, I powered the grid line and the voltage reading was accurate with a plus or minus 2 voltage difference, which is okay for now. I powered the generator source line and I got an accurate reading, and same was applicable for the inverter source. For the casing of this project, I measured out every external component that I would love to put out on the 6x9 adaptable bus. And after coupling these components into the bus, I now have the assembly looking just like this. Turning on the system, I have the circuit boot and started sensing available sources. For the first test which I'm going to conduct, I'm going to use jumper wires for each sources, just as I have the yellow and black wire for the solar source, blue and black wire for the generator source, and red and black for the grid line. All the black neutral wires of all sources are connected together in the same rail on the breadboard, just as you can see, and I have them hooked up to the single AC line neutral source on the blue crocodile clip. The red crocodile clip wire is the single source AC live wire, which I'm going to momentarily connect each source live wire to, and finally I'm going to be using a white bulb as the load. Connecting the white bulb to the load output, I'm now ready to test the system. For the first test, I hooked up the blue wire, which is the generator line, to the AC line sources in order to complete its AC line circuit. After a few seconds, which I programmed into the microcontroller, the line got triggered just as I have my output turned on and the LCD displays the value for this source. Next, I hooked up the solar line, which is the yellow wire, to the AC source, and from the program line of code, the buzzer alarm will trigger for 10 seconds before switching the line. Just as you can see, the load shifted from the generator relay line to the solar relay line, and this happened instantly without having the bulb turn off. Now, I am going to do the same thing for the red line, which I have as the grid line. The buzzer triggered again for 10 seconds and switched the load to the grid line instantly. To confirm this switching, I removed the yellow and the blue line first of all, and as you can see, the bulb is still on until I remove the red wire. For the generator automatic switch off control, I connected the output wire to the generator switch while I have it hooked up onto the generator, and also the output AC voltage from the generator I have connected to the system. Now I turn the generator on for test. I have the system now and every part of the whole connection is down, so we are going to start with the generator. So we run the generator. So the gen is running and the load is connected to the gen line. So what I'm going to do next is to connect the grid line. This is the wire for the grid line, and cut and socket. So let's check it out. The alarm indicates that the grid line is on. In 2 seconds, this will turn on. And as such, this actually went on because I have the grid line turned on, and after 10 seconds using the alarm indicator just to let me know that the grid line is on, after 10 seconds the system was able to switch into the grid line, and just as you can see, this man didn't turn off, but it was able to turn off the generator automatically, and that is the system working, and I'm so excited to have this project. It's good to have completed this project, and I'm excited at the outcome. You can find all the relevant design information for this project, which include the schematic diagram, the block diagram, the Arduino programming, all available on the video description. Over time, I've been able to build other design with respect to this project, just as I have an IoT design model working here in my space. This model monitors my load, energy, and also the corresponding billing I should pay per month. Feel free to drop your thoughts about this project on the comment section, as I would love to read them. And thank you so much for watching this video, and I will see you on the next project. Do have a blissful day.